Assalamualaikum and good day everyone. Thank you for listening to the recorded lecture. So today we're going to have a look into the third BJT DC analysis. Alright, the third bias circuit configuration, which is known as voltage divider bias circuit. Okay. Before we go to this part, let's do some recap, quick revision. Okay, so last 2 weeks ago, we have learned about fixed bias circuit, okay, as well as emitter stabilized bias circuit. So this is an example of the fixed bias circuit. So we have here is RC, RB, and no RE at E terminal. On the other hand, the emitter stabilized bias circuit, okay, we have an additional RE at the E terminal. So the reason why we put RE here is the reason is very simple, okay, to stabilize the BJT bias circuit, okay. So if you still remember, I have given you a mini assignment, okay, for you to do to answer 2 questions in activity 3.13, which is question number 4 and question number 8. Okay, so let's have a look at several answers from your friend here. Okay, I cannot pick this one. This upside down, difficult to show you guys. Okay, maybe this one. This is Abdurrahim. Okay. So question number 4 is regarding the fixed bias circuit. Okay, so what you need to do in this homework is to determine the biasing voltage as well as current for the BJT fixed bias circuit. So we have RC 1K, RB 414 kilo ohms with beta 75, and VBE is assumed to be 0.7 volts. Okay. So as I told you before, you need to solve it using KVL. First at input section and the other one is at output section. Okay. So again, I would like to remind you that the plus VCC here, or plus 20 volts in this example, okay, is connected to RC and as well as to RB. But the RB and RC, they are not joined together. Okay, they are separate. Okay, you must split it. So if you redraw it again, okay, so the current or the latest drawing for the circuit is, okay, plus VCC connected to RB and another plus VCC connected to RC. You can split the connection between power supply and the RB as well as with RC. And another important point that you need to remember is that you need to put, okay, or draw or whatever you name it, the plus and minus VCE as well as plus and minus VBE. Okay. Alright. So the current flow through RB through VBE, we call it input section atau or input loop. Okay. Whereby another current that flow, which is IC, going through RC plus VCE to the ground, we call this one as an output loop. Okay. So let's see the solution here. So first of all, you need to apply KVL at input section. So we have here is minus VCC plus IB times RB plus VBE equals to 0. Okay, so you can get the IB here Alright, IB you should get 46.62 microampere. And then from here, you can calculate the IC using this relationship. Alright, IC equals to beta IB. So beta is given here, which is 75, times IB 46.62 microampere, you will get 3.5 milliampere. Okay. Then, next step is to apply KVL at output section. So that is very simple. Minus VCC plus IC times RC plus VCE equals to 0. Okay, so you should get VCE equals to 16.5 volt. Okay, that is for fixed bias circuit. Very easy. Now we move to question number 8. Okay, question number 8 is emitter stabilized bias circuit. So we have an additional RE here at the E terminal. So what the question asks you to do is to calculate alpha, VE, VC and VCE, okay, for the following circuit, given VBE is 0.7 volts and beta is 200, okay. So you, in case that the alpha is not given, the alpha formula is not given in the question, yeah, usually, so you need to remember or memorize it. So here alpha is equals to beta over beta plus 1. So you should get 0.995 here. Okay, and then again, to obtain the VCE, VE and VC, alright, you need to identify the input section and output loop section. So here, Ain has had divided the circuit, split the power supply. Alright, one is connected to RB and another one to RC. And also put the plus minus VCE and plus minus VBE here. So again, you need to apply KVL at input section. Very easy. It is minus VCC plus IBRB plus VBE plus, now you have another additional RE here, so it must be IE times RE equals to 0. So IE, okay, we have another formula that relate IE with IB, so use it. Okay, so it becomes IE equals to beta plus 1 IB. So you put, or you replace IE here with the current or similar formula. Okay, so it becomes minus VCC plus IBRB plus VBE plus beta plus 1 IBRE. So the next step is you make IB, alright, as your main concern here. Okay, then you rearrange the other equations, so you will get the result. IB is 30.15 microampere. Okay, next step is, again, you need to get IC. So IC is beta IB, so that is the answer over there. And then next step, you need to apply KVL at output loop section. So very simple. It's just that you have another voltage drop that you need to consider, which is IE/RE. Okay. For KVL at output section, you need to assume IE approximately to IC. Okay. So you replace IE here with IC. You rearrange the equation to get the VCE equals to 6.73 volt. Okay, that, I hope you are clear about that. It's just that if you, for example, if you do it step by step, VCC minus ICRC minus ICRE, you most probably cannot get 6.73 volt. Okay, for example, let me check, yeah, your other friends. For example, if you do if you don't combine it, okay, the result might be not so accurate as the results in the module. Okay, here we can see that what Rahim did is Rahim do it one by one. Okay, 20 minus ICRC minus IERE. So the result yield is 6.756, something like that lah. But again, if you combine it, because they share the same IC, the same current IC for RC and REC, so you can combine it, so you'll get the result as accurate as in the book or in the module. Okay. Next, you calculate the VCE, very easy. The VC. So you got VCE and VE already. So what you can do, you just rearrange the equation to get the VC, and finally is the VE. Okay. I hope you still you can remember the important formula. Alright. So now we move back to, okay, before I forget, I want to say something about DC load line. Okay. Okay, here, this is an example of DC load line. Alright. For what type of circuit is this? Is it for fixed bias circuit or emitter stabilized bias circuit? I hope you answer it, the first one, fixed bias circuit. Why I said so? Because you can see the VCC over RC here, the point at y-axis, okay? This is referring to fixed bias circuit because there is no RE here, okay? But another one, example here, the load line analysis here, VCC over RC plus RE. This one is for the emitter stabilized bias circuit because there is an additional RE here. The rest is similar. For example, the point at x-axis here or at VCE axis here is VCC. Okay, similar like here, VCC. Alright. How can you draw the DC load line here? You need to use, okay, you need to use KVL at input section or KVL at output section. Okay, correct. You need to use KVL at output section because at output section only there is exists IC and VCE. Alright. So the DC load line must be drawn using output loop, KVL at output loop. Okay. So you must remember the output characteristic for BJT is this graph, IC versus VCE. Okay, the blue line here indicates the IB curve, okay, or IB current. Okay, so once you calculate the IB, for example, okay, in this example, you calculate IB equals to 46.62 microampere. Okay, so we assume that IBQ here happens, okay, let me rephrase. Okay, so you imagine the IBQ, alright, IBQ here is this amount, okay, 46.62 microampere. So the Q point, alright, you can determine the Q point once the DC load line here intersect with the desired IBQ here. Alright, so let's say if your calculated IB is not 46, for example 60, so the 60 microampere is right here, so your Q point is already shifted to another level. Okay, the Q point will be here. Okay, now let's stick to the current example. So assume IBQ is 46.6 microampere. You draw the DC load line here. Alright, so you can estimate the Q point here. It will occur at VCEQ and ICQ here. Okay, understand? If not clear, you can come and meet me later. Okay. Alright. The same thing happened for DC load line for emitter stabilized by circuit. Okay. Again, to draw the DC load line, you need to use or apply the KVL at output section. Okay, because at output section only we have IC and VCE existed, right? So again, I want you to remember, please remember, okay, this is important. It might appear in your final exam question, okay? You need to remember how can you able to draw the DC load line. For example, emitter stabilized by circuit. So make sure that you know how to answer the question, okay? Or maybe the question asks you how the DC load line can be drawn for fixed by circuit. So make sure you are able to show an example like this, okay? We have VCC over RC here, and VCC at VCE axis. Alright, so the load line can only be drawn if we solve the KVL at output loop section. Okay. So now let's move back to our current issue, right? Current voltage divider bias circuit analysis. Okay. So in voltage divider bias circuit, or I name it in short VDB, we have another resistor connected in between the base terminal and the ground. So we name it as R2. The rest is same, R1, RC, and RE. Okay. In order to solve the voltage divider bias circuit, there is a rule of thumb that you need to memorize or understand. Okay. In order to solve VDB, there are two methods can be employed. The first one is the approximate analysis, and the second one is the exact analysis. Just now I said about rule of thumb, right? So how can you know that which methods that you can use to solve the voltage divider bias circuit? When to use approximate analysis? Okay, when can you use exact analysis to solve VDB circuit? So what you need to remember is that you need to use the first one, the first and only rule of thumb is you need to calculate beta RE, right? Is it beta RE bigger or smaller than 10 times R2? Okay, understand? Right? First of all, calculate beta RE. Identify, is it greater or less than 10 times R2? So, if the beta RE, okay, beta RE, you know beta RE, right? Okay, beta usually given in the question. So, RE is referring to the resistor at E terminal here. So, calculate it and then calculate 10 times R2. Where is R2? R2 is over here. So 10 times R2. And then comparing which one is greater, which one is smaller. Okay, so if beta R is greater than 10 times R2, you use approximate analysis. If it is less than 10 R2, you use exact analysis. Okay, is that clear? Alright, now let's have a look how to solve using solve VDB using approximate analysis. Okay, point number 2 here. We have learned that VBE is equal to VB minus VE. And then in this case, for VDB only, okay, we assume that VBE equals to 0. When VBE equals to 0, what happens is that VB will equals to VE, right? But VE is equals to IE times RE. And IE we can write down as beta plus 1 IB. So the VE here, okay, we can write down as RI IB. RI is beta plus 1 RE. So in this case, the RI here is assumed to be approximately equals to beta RE. You see? These things is come back to the rule of thumb, beta RE. So, if beta RE is bigger, when you calculate, it is bigger than 10 R2. So, once the beta RE is bigger than 10 R2, we can draw a simplified voltage divider circuit at input section based on point 2 above. So, point 2 here, okay? So, from this circuit, you can draw a simplified one. Okay, here I neglect the output loop section, the RC. I only draw VCC, R1, R2, RE, and ground. Okay, so this one you need to remember. Okay, you need to practice to draw it. So you have R1 connected to VCC, the negative supply of VCC connected to ground, and then we have R2 which is definitely connected, obviously connected to ground as well. And then the RE here, since we assume VBE is equals to 0, means that there is no BJT here. We assume no BJT. Alright, no BJT, so we can directly connect the RE. Now it becomes RI, okay? Because RE times beta plus 1, right? We already defined it. So just connected it to VB here. VB is right here. It's in between those R1, R2, and B terminal. Okay? So this is VB. Then we assume, okay, RI is greater than R2, obviously, because this is our current assumption, beta RE greater than 10 times R2. Then we can assume that I1 that flow through R1 is equal to I2 that flow through R2. Since RI is too big, okay, you must understand, if there is a current here, okay, in the intersection or in the junction here, decide where he wants to go. Is it through R2 or RI? But again, since RI is getting, the value is really big, okay, bigger than R2, so the current decide not to go through RI, okay, less obstacle, alright? So the whole I1 here will go through R2. That is why we assume that I1 is equals to I2. So now you can calculate the VB at input section. VB is the voltage across R2, right? VB is the voltage across R2. So you can use voltage divider rule. R2 equals to R2 plus R1 times VCC, right? Then you can calculate the KVL at output section. This is the last step. So approximate analysis is very simple. Okay, if the worst case, if you cannot understand the fundamental here, at least you can straight away memorize the formula. Very easy. Okay, but you need to draw the correct simplified voltage divider circuit. Okay, if this wrong, all calculation will be wrong. So the KVL similar to emitter stabilized by circuit. Okay, now we move to exact analysis. Just now approximate analysis emphasized on beta RE greater than 10 R2, but for exact analysis beta RE must be less or smaller than 10 R2. Exact analysis approach is different to approximate analysis. In exact analysis, you must do or perform or calculate, okay, the Thevenin at input section. Thevenin at input section. Once you finish calculate the Thevenin values, okay, only then you can proceed to applying KVL at output section. Okay. Now let's see what we have here. So we have similar VDB circuit configuration. Alright. Again we have VB here, similar as approximate analysis. It's just that in this case, okay, listen carefully. You need to redraw it. Okay. Again, we know previously that VCC is connected to R1 and is connected to RC, but R1 and RC does not join together. So what you can do is redraw again the circuit. You connect R1 to VCC here, the negative power supply connected to the ground. R1 and R2 we have VB here. Then you draw another BJT here. In approximate analysis just now, there is no BJT. Why? Because we assume that VBE is equals to 0. So when VBE is 0, so no BJT. Understand? You can understand like that lah. Okay. Okay, for here, in this part, for exact analysis, VB, this is VB, okay, and then connected to BJT. For the dash line here, okay, the dash line here, okay, you need to apply Thevenin, okay, by looking from this side, this direction. Okay, how to solve it? KVL at input section. You need to open the base terminal and then calculate VTH using voltage divider rule. So very simple. You disconnect the BJT here, BJT and RE, disconnect, because we are looking from this direction, so we disconnect all of it. On the left, R1, R2, ground and VCC. So now you can calculate the VTH, right? So VTH is equals to VR2 or VB, okay? R2 equals over R2 plus R1 times VCC, okay? So you manage to get VTH. Second step, you must calculate RTH. VTH comes together with RTH, yeah? How to do that? You need to short circuit the power supply. So power supply is the voltage power supply, you need to short circuit. If the power supply is the current power supply, you need to what? Open circuit. So this one you short circuit it. The rest is remain R1 and R2. So R1 and R2 now is in parallel position. So you can calculate the RTH using this formula. So straight away, you just memorize this formula, R1 times R2 over R1 plus R2. No need to use 1 over R equals to 1 over R1 plus blah blah blah. Okay, you save your time. Memorize this. This is only applied for parallel resistors. Okay, once you obtain the VTH and RTH, what you need to do is that you plug in them back to the BJT and RE circuit. Just now you remove them. Now you plug in the new VTH and RTH into the base terminal. Okay, so this is what happened. You just plug in VTH here, RTH connected to the base terminal. So it's very easy. You can now calculate the KVL at input section. It is minus VTH plus IB RTH plus VBE plus IE RE. Don't forget to remark the plus minus VCE and plus minus VBE. Okay, again, same assumption. IE equals to beta plus 1 IB. The rest, I think you already know. Just remember that no longer VCC available at IP section. Okay. Again, I remind you, the VCC is not existed anymore. Only left is VTH because we already simplify using Thevenin voltage. So must be in input section is VTH. If I see VCC, definitely I give you 0 because you don't understand the Thevenin theorem concept. Okay, so minus VTH plus IB blah blah blah. This one you already know. Then you will get IB value here at input section. So at output section, we have KVL here. Again, very easy. We have done it many times before. Okay, you need to remember assumption that you need to use IE approximate to IC, and then you will get VCE. Okay. Meanwhile, other voltages, for example, VE, you can calculate using IE RE. VC, you can calculate either using VCC minus ICRC. Where is VC? Where is VC? Okay, VC is somewhere here. Okay, somewhere around here. It is a combination. Okay, you have two formula to use. Another is VCC minus ICRC. VCC minus ICRC, you will get VCE. Okay, or otherwise you can use VC equals to VCE plus IERE. Okay, so you choose which one is easy to use. Okay, which information that you have in your hands, utilize it and decide which one you can or you're able to use. Next is VB. Okay, also got two equations here or two formulas, right? Or lastly, you can use VB equals to VTH minus IB RTH. So means that you have for VB you have three formula that you can use. Either one will yield the same result. Okay, that's it for now. I will give you an exercise. Please complete it. Okay, the questions that I will give to you, okay, you need to submit it by Thursday, this coming Thursday. Okay, let me check the date. Okay, you should submit your answers by 13th of April. Okay, by Thursday before midnight. Okay, this is important because these questions are going to pop up out. Okay, either in your upcoming test 2 or during final, or maybe it will appear in both. Okay, so I hope you try to make use of your time to finish up. Alright? Okay, thank you for listening.